Okay. So hope you can hear me. Welcome to another online seminar of EPICentre. Today we have Rafael Fernández, who is going to talk about a decision-making framework for school infrastructure improvement. As usual, I'll give a short introduction, then Rafael will give the presentation, and there's always time for your questions. So Rafael Fernández is a PhD candidate at University of the Andes in Colombia, and he's currently visiting UCL's EPICentre Research Group, collaborating with Professor Dina Dayala. He's a civil engineer and holds a master's degree in seismic and structural engineering. He has worked on several disaster risk management projects for different types of hazard in countries such as Peru, Ecuador, Colombia, all the way to Dominican Republic, Bolivia, and Barbados. Rafael has also been part of the team that developed the Global Library of School Infrastructure, GLOSSY, for the World Bank. Rafael, it's an honor having you here. Whenever you're ready, please share your screen and the floor will be all yours.
Thank you very much, Arash, for that kind introduction, and thank you all for connecting. I'm sharing now my screen. Can you confirm, Arash, if you can see it?
Yeah, I can see your screen, and yeah, all is good.
Perfect. Thank you very much. Well,
thank you.
Hello, everyone. As Arash was mentioning, my name is Rafael Fernández, and today I'm going to talk to you a little bit about my PhD research project, which is titled A Decision-Making Framework for School Infrastructure Improvement. So the idea today is to show a little bit how is the method that I have developed in my research dissertation, and also to show you some of the results that we are developing at the moment. But first of all, I want to start with the beginning and how and why we should research this type of improvements, or why school infrastructure should be improved. And that starts, of course, with the Sustainable Development Goals, and in particular with the goal number 4, which tries to ensure an inclusive and equitable quality education and promote lifelong learning opportunities for all. And in here, the word or the words that are very important is quality education. It's just not giving education without any condition. The education should be a very with a lot of quality. And in that sense, it's very important to assure that, because also guaranteeing this quality education will also have an impact in all other SDGs, but in particular, for example, reducing poverty, improving decent work and economic growth, gender equality, it will reduce inequalities, and so on. And the problem in here is that there's a very high inequality in educations in the countries, and depend on the different income level, they will have different conditions currently. So based in UNESCO data, we can, for example, see how is the completion rate by country if we group them by income level. So for example, we can see that the situation is very critical for low-income countries and also for middle-income countries. As for example, you can see that the completion rate for the upper secondary level, it's only 28% in comparison to 64% in high-income countries. So this represents a disadvantage for students that currently are in low and middle-income countries. So we need to target that, and we need to therefore offer a much quality education. And for that, we need to understand what are the barriers for this to guarantee a better quality education. And in that sense, the NGO Educate a Child, for example, propose these 9 barriers. First, they start with poverty, also with challenging geographies. They talk about post-conflict insecurity, refugees, about gender also, and how this affects quality, infrastructure, resources itself by the quality of the learning process. And also they talk about climate change. But in particular, we are interested in how infrastructure will affect quality in that sense, since this PhD project was designed to target infrastructure, and by improving infrastructure, improving quality at a broader level, education quality at a broader level. So in that sense, a lot of people have researched the impact of school infrastructure on learning. In particular, there are a lot of reports by the World Bank in which they assess how the functional aspects of infrastructure make the learning environment better for the students. There is also the comprehensive school safety framework developed by UNICEF, UNESCO, different NGOs such as Save the Children and other organizations, in which they talk how infrastructure should not only be functional, but also it need to be safe, because most of the schools are prone in a hazard-prone areas, and in that sense, it's very important to ensure the quality of the buildings in terms of their safety against, for example, earthquakes or hurricanes. There is also something very important related to the water and sanitation hygiene, and for example, in the sanitary facilities, and how these affect also gender inequality, and how important it is to have good quality and sufficient quantity of bathrooms for both girls and boys, for example. And there's also several more reports that I'm not going to mention in detail. I will just finish this short literature review with the report made by the IDB, the Inter-American Development Bank, in which they establish how the schools should be in the 21st century, and how these schools need to offer a better quality infrastructure, and therefore with this, a better quality education. So based on this, we need to establish that infrastructure, and in particular in this project, we are focused on existing infrastructure rather than in new infrastructure. We are trying to analyze how is the existing infrastructure and how we can improve it. And in that sense, we need that the existing infrastructure will be more functional in the sense that you need to offer sufficient space for learning. You need to offer comfortable classrooms. You need to offer also adequate sanitary facilities. You need to offer to the students connectivity in terms of electricity and also in terms of internet connections. And the school should be durable also in time. And as I mentioned, schools should also be safe in relation, for example, to natural hazards. One of the most studied hazard is the earthquake hazard, but there's also tropical cyclones, there's flooding, there's landslides, and even wildfires or other type of hazards that should be analyzed. And also there are health hazards, for example, as what we have seen with the COVID-19 pandemic. And there are also man-made hazards that should be included in the decision-making process when we are talking about infrastructure. So therefore, and with this problem in mind, the main objective of this research is to propose a methodological framework for physical school infrastructure improvement. And there are several specific objectives. The first one is to understand the quality of buildings. And for this, we need to develop a building quality index, but this index should have a holistic perspective. We cannot see this index just as if the schools are safe or if the schools are functional. We need to integrate all those aspects to understand quality from this holistic perspective. We need also to develop a grouping system or a clustering procedure to identify main typologies, because the main objective or the main idea of this is to develop large-scale interventions, and that cannot be done building by building. We need to identify groups of similar groups of buildings of similar characteristics, and to these buildings we can then design different intervention alternatives. We also need to understand how the interventions would increase the quality of the infrastructure, and also how does this intervention, or how much this intervention will cost. And for this, it's important to associate the increase of quality with the increase of the building quality index that we define at the beginning. And at the end, with all the set of interventions, we need to prioritize them, because budget usually is not unlimited. So what we have in here is limited budget characteristics, and therefore we need to identify the best interventions that increase the most the quality at the lowest cost possible. And at the end, the last objective is to apply this method that we are proposing in this project in 2 case studies, one at country level and the other at city level. And today I'm going to show you the results for the city level application. But first I want to show you the methodology that we are proposing and how these different models will connect. So first we have a model that is the model 0 in which we process all the existing data. And for this is important to differentiate the different agents that we are analyzing in here. First, there are schools. There's a number of schools in a particular region, and each one of these schools will be comprised by several buildings. It can be one or it can be more, and depending on the characteristics and the amount of students, this will vary, and the characteristics of each region will vary, will make different the characteristics of each building. So we have 2 types of information. We can divide the information at the school level information. For example, we can analyze how many students and how much built area do I have in a school, for example, or how many bathrooms do I have in a particular school. And there's also information at building level. For example, I can analyze different characteristics such as comfort. For example, it's important to know if in each one of the buildings, and in particular in each one of the classrooms, there's enough ventilation, if the lighting is enough. And there's also another characteristic, which is safety, that should be assessed at building level and not at the school level, because a school can have several buildings and each building can behave and may have been built, for example, at different ages. And so it's very different to assess safety to like against different hazards, but at a building level. And with this information, we can then obtain, for example, a taxonomy to categorize each one of the schools when we are talking at school level characteristics, and a different taxonomy to assess the building level characteristics. So in that sense, we need to characterize for each one of the buildings all the taxonomies related to safety, for example, in the case if we are, for example, analyzing a region in which tropical cyclones are very important and also the earthquake hazard is also very important, then I will need to develop 2 taxonomies, one for each of the hazards, and also a taxonomy for functional characteristics or for related to comfort characteristics at building level. And I also can make something similar at school level for the functional taxonomy. So once I have all this information, all the data processed, and all the taxonomies identified at building and at the school level, the next step is what we define in Model 1, the Building Quality Index. And this Building Quality Index, as name suggests, is an index that tries to measure how good is the quality of that particular buildings in terms of the learning environment that it gives. And for this, we need to analyze several attributes or several criteria related, for example, to functional aspects or to safety aspects. And at the end, this building quality index, or BQI, will be the sum of the score of each one of these attributes multiplied by a weight that depend directly on the decision-making preferences. And in that sense, we will see in a few slides how this decision-making preference will affect at the end the results of applying this method. Then we have the Model 2, which refers to the clustering procedure. In here, we have 2 different levels. First, we have the building level taxonomies. So we have the set of all buildings characterized each one by one taxonomy. And we can have not only one taxonomy, but several taxonomies in here. And we have another set of taxonomies which refer to school level characteristics. And for each one of these sets, we need to apply a clustering algorithm. In this case, we are going to show in a few, I'm going to show in a few slides what we proposed in here, which is a clustering algorithm, which is also a machine learning procedure to obtain these particular clusters. Once we have these clusters of buildings of similar characteristics, then we can define in Model 3 the generic intervention that we can apply in here. For example, if we are talking about the seismic hazard, we can have a cluster of high vulnerable buildings in which the generic intervention could be the replacement of that building. And we can have also an intermediate cluster in which we can apply a particular retrofitting to all of its members or all of its buildings. And that will also be a generic intervention that should be established in here. But these interventions, they are not particular for each one of the buildings, but rather for the characteristics of the cluster. So then we need to translate that generic intervention into a particular intervention to each one of the buildings. And for this, we need to assess two things, which are the most important things. First is by applying that generic intervention to a particular building, how much would the BQI increase? That can be translated into, for example, the benefits. And we should also identify how much will it cost, because, for example, if I have to retrofit a building with 8 classrooms, it will be much more costly than retrofitting a building half of that size. So in that sense, we can translate all the generic interventions by particular interventions to each one of the members of the cluster. And we can do the similar process to all the school level interventions. And in this case, we are going to have the increase of quality of all the buildings belonging to that school, and also the total cost of that intervention. And at the end, with this particular building and school level interventions, what we are developing, or what we have now, is a big bag of interventions. So this can be classified as an intervention database, and together with some constraints, for example, a budget constraint or a particular minimum quality constraint, as we will see in a few slides, we can then develop an optimization model that will result on a set of optimal interventions. And this set of optimal interventions will be the main output of the decision-making framework that we are proposing. So this is like the big picture of the methodology that we are proposing in this research project. And now I'm going to go to each one of the models to show first how like the theory behind the model very fast, and then we will see the application into the Cali case study. So first, the model 0. It's named model 0 because the decision-making framework that is proposed in here starts with all the data characterized. And what we have in here is, as mentioned before, different type of leveled information. We have information by building that can be, for example, the structural characteristics of the buildings, the material, the structural system, or any other important structural characteristics, and also the risk metrics for the main hazard. For example, we can obtain the data from risk assessment that was done to that particular portfolio of buildings. And we also can obtain, for example, information related to its functional characteristics. For example, architectural characteristics of the building, how large are the windows, how open are them, how, for example, if the doors are enough for the classroom, and so on. And we can also, for example, know how is the current condition of the building, or if the equipment is adequate for the particular school that we are analyzing. And with this, we can therefore derive safety taxonomies or functional taxonomies, but at building level. On the other side, we have a school level information. In here, we can obtain, for example, general architectural characteristics of the school by itself, like where are the buildings, where are the bathrooms, the accessibility, and so on. And also the condition of each one of the facilities. For example, in relation to the bathrooms, how many bathrooms could this particular school have, and what is the condition of those bathrooms? Also, how many students does this school have, and it is okay for the total built area, or there's a need, for example, of more classrooms or less. And in that sense, we can also define, for example, a functional taxonomy, but now at the school level, that will assess or categorize those characteristics that will be associated to the school level characteristics. In particular, for the Cali case study, this was based on a project that was done in 2019 by Uni Andes and the Global Program for Safer Schools. And in here, we took that database in which some information was deriving here. For example, a risk assessment was done, a seismic risk assessment, and also some field surveys that were used to identify some of the functional characteristics of the school facilities. So just to have this in mind, the Cali public school infrastructure is comprised by around 300 school facilities. These schools serve around 92,000 of students, and the number of buildings is 1,200 to have in mind the size of the portfolio that we are analyzing in here. And in this particular case study, we obtain one seismic hazard taxonomy, which can be analyzed at building level, as I mentioned before. There's a functional taxonomy at building level also, and we also have a functional taxonomy, but at school level. So we are going to deal from now on with these three taxonomies, and these will be implemented in all the decision-making framework that I am showing in this presentation. So if we go back, we already saw what is the data processing. Now we have all the schools and the buildings characterized, and we have the different taxonomies. So the next step is to assess the building quality index. And what we want to measure in here is exactly how quality is in each one of the buildings, and how this can be analyzed from a holistic perspective. And what we apply is a multi-criteria approach. So at the end, this building quality index is an index that is comprised by several attributes. The first hierarchy division is the functionality and the safety, and each one of them will divide into additional elements. So for example, when we talk about functionality, we can talk about the student density, about bathrooms quality or density, about the lighting or the ventilation in each one of the schools. And when we talk about the safety, we can talk about earthquakes, about hurricanes, floods, landslides, wildfires, or any other type of hazard. So for example, if I am trying to analyze a country or a portfolio located in the Caribbean, maybe for me it will be very interesting to analyze the hurricane hazard, but also the earthquake hazard. But for example, if I am going to assess a region near the Amazonian forest, maybe it will be more interesting to analyze the wildfire risk rather than a hurricane that will not affect that particular area. So in this case, we have like this building quality index that should be modified for each one of the case studies. And each one of these attributes will at the end have a score that will be normalized from 0 to 1 and a particular weight. And the weight will be used to define this BQI, which will be defined as the sum of the multiplication of the score to the weight. And this weight, how can I obtain? At the end, the weight is an input to this model because will be directly associated with the decision-making profile. So for example, if you are doing this from a Ministry of Education in a high hazard prone area, maybe you will give more information or more weight to the safety criteria. And if you are in a country with very low risk against natural hazards, then maybe you will give more weight to functionality. So the idea is to have the door open, that this decision-making framework will be applied by different people, and the results, of course, will vary in that sense. So in the particular Cali study case, we modified this building quality index. We consider several functional parameters as shown in this slide. And in terms of safety, we consider the earthquake risk level, which was obtained from the probabilistic risk assessment that was done in 2019. And just to illustrate how the method works, I'm going to show you the result for two different decision profiles. One in which the functionality will be prioritized. In that sense, we are giving more weight to all the functional aspects. Around 90% of the weight will go to that like hierarchy or criteria of functionality. And then we will have the opposite decision profile, which will give more weight to the safety consideration, and in this case, for the earthquake risk level. So if we first use the normalized rating for each one of those criteria, then we can integrate that into the building quality index, and in here you can see the distribution for each one of the profiles. So for example, we can see that the dispersion in the decision profile 1, the functional decision profile, is lower than the dispersion that we have in the safety decision profile. And also the mean, the maximum and the minimum will be different in each case. For example, for the decision profile 1, we have a building quality index mean of around 0.6 BQI points, which go from 0 to 1, being 1 the most quality or the most quality possible building, and 0 the worst quality possible. And when we analyze the decision profile 2, we have a mean that is lower 0.6, around 0.55. And in that sense, we also have different, a range of different ratings for all the buildings. Then if we go back to the picture, the next step is the model 2, the clustering. And what we want to answer with this clustering procedure is how the buildings can be grouped to identify the main typologies. And we need to group these buildings and identify these main typologies to develop large-scale interventions. So in that sense, we apply in here a machine learning algorithm, which name is a Bernoulli mixture model. This can be classified as a probabilistic model for soft clustering. And I don't want to go into the technical details, but very fast, what we're doing here is first start with a taxonomic categorical database. Then we pre-process the data, translating each one of these taxonomy strings into binary vectors in a process that is commonly known as one-hot encoding. And then we define a number K of cluster and we apply the algorithm. But this algorithm uses as distance metric the likelihood of an element to belong to a cluster with a fixed Bernoulli distribution. And at the end, this is a repetitive process in which I need to start varying the number of clusters until I find a distribution which is logical from different point of view. So for example, I can start doing or applying this algorithm with 2 clusters to analyze if the distribution of the portfolio can be divided into 2 clusters. But if I found that the results are not good enough, then I need to try with 3 clusters, 4 clusters, and I will continue this process until I have a good distribution of the data. So in the Cali case study, we use the seismic taxonomy. This is the seismic taxonomy developed in the Global Library of School Infrastructure. So we have 12 parameters. We then obtain the taxonomy string combinations for each one of the buildings in the portfolio. And we took the database, we applied the Bernoulli mixture model, the clustering algorithm, and through an iterative process, we find the number of clusters that results in logical distribution. So in this particular case, we found that all the portfolio can be divided into 8 clusters. In this table that I am presenting in here, each one of the clusters is one horizontal bar. For example, this cluster is comprised by 100% of particular typologies. We have 100% of adobe buildings, and with unreinforced masonry poor design buildings. So for example, in here, we have a cluster that is comprised with the high vulnerable buildings, which maybe need to be replaced. And I need to continue analyzing each one of these clusters to see if all of them are logical and the distribution makes sense in relation to the type of intervention that I am going to apply. So for example, in this last one, I can see that there are all the typologies with a high design in terms of the seismic design level. So this will be a cluster in which no interventions will be required for the members of that particular cluster. And this process was applied also to the functional taxonomy at building level. So in this functional taxonomy, we analyze another type of characteristics, for example, the ventilation and the illumination of each one of the buildings, the type of interior finishes and the type of furniture, And once we have all the taxonomy string combinations, and again, in here by each one of the buildings, we apply the Bernoulli mixture model, we obtain different distribution of clusters, and we finally found that 6 clusters was a good distribution for this particular building taxonomy, functional building taxonomy. And finally, for the last taxonomy, we have now a functional taxonomy at school level. So in here, what we want to characterize is the density, the student density, the bathroom quality, which is also important to see if the intervention should target, for example, improving the current bathrooms or developing new bathrooms, water distribution and sewerage access, and internet and phone connection. And in here, we also obtain a database of taxonomy strings, but this will be a shorter database, since this is a database in which I will have one taxonomy string for each one of the school facilities, rather than each one of the building facilities as in the previous cases. In here, at the end, we are working with the same type of data, so we apply the same Bernoulli mixture model, and in here we find that the number of clusters is 20. And at the end, what happened with this taxonomy is that around like what happened at the end is that each one of the clusters is comprised by one particular typology. So once we have this, then the next step is to define the intervention that will apply to each one of those clusters. So we need to understand how these interventions will increase the quality and how much does this intervention will cost. So the main objective of this model is at the end to have a database of interventions applicable to all the buildings and applicable also at a school level. So we have taxonomies per school building, we have taxonomies per school facility, and we have a clustering procedure that we done in the previous step. And for each one of the clusters, we will have one particular intervention for each one of the taxonomies. And at school level, we will have also one intervention for each one of the clusters that will be applied to each one of the schools belonging to that particular cluster. And there are some considerations that are important to consider in here. And is that, for example, if I am analyzing a replacement of a building due to the vulnerability associated with the seismic hazard, then the other type of interventions will not be considered, because I'm going to build a new school that complies all the standards and therefore will not need any other type of interventions. And also something very important is that at this moment, we are not considering the reduction in cost for doing intervention at the same time. So this can be understood like a top tier level of investment that is needed. Maybe some type of reduction can be achieved, but the idea of this is to have a very generic picture of how we can do this type of budget allocation. So I'm not going to each one of the clusters, but for each one of the taxonomies, for example, if you remember for the seismic taxonomy, we had 8 clusters. So for each one of the clusters, we identify the intervention type, if it's a replacement, if it's a retrofitting, a minor retrofitting, or an extensive retrofitting, and the unitary cost of this. So we can obtain the cost, for example, of retrofitting 1 square meter, and this information will be then used to apply this unitary cost to the real size of each one of the buildings. The same process was done for the functional taxonomy at building level and for the functional taxonomy at school level, with several interventions type for each one of the clusters. So at the end, what we have in here is a set, like a big set of interventions. In here, we have a table in which each one of the lines is one building. We have 1,200 lines in this case. And for each one of these lines, we will have a particular intervention for each one of the taxonomies that we consider. So for example, in blue, you can see the seismic taxonomy, the seismic interventions at building level. In the yellow one, you can see the functional interventions at building level. And in the orange one, you can see the functional intervention, but at school level. So that's why you can see that the intervention will apply to all the buildings in that particular school. And in red, you can see, for example, what I was referring, that this building will be replaced due to the seismic intervention, and therefore the intervention or the functional intervention is set in 0 in this case. But it's important to see that this is a set of all the possible interventions, but maybe some interventions are not going to be useful. For example, if I want to retrofit a building in a low seismic area, maybe the increase in the building quality index will not be as high as the same retrofitting applying to a very similar building, but that is located in a high seismic area. So in that sense, it's very important to not only characterize the cost, but also the increase in quality. And in this case, this is translated into the increase of the building quality index. So for this set of interventions, we will have a total cost of around $170 million, with a total increase of BQI or benefits in that sums 272 key points. So remember that we have 2 decision profiles. So the results that I was showing before refer to the results obtained with the first decision profile that was prioritizing the functional condition. But if we go to the second decision profile, in which we are prioritizing or giving more weight or more importance to safety, then we will have a different data set. At the end, the interventions will be the same and the cost will be the same. You can see that for both decision profile, the cost of intervention is the same, but now the total BQR improvement or the possible benefits will be different because I am now analyzing from a different perspective. This can be also analyzed or understand as different views of the same problem. So in this case, we have 336 BQI points of gap of improvement. So with this database, the next step and the final step of this methodology is the module 4, which is the optimization. What we want to know in here is how to prioritize the interventions in order to maximize the quality of the infrastructure for a fixed level of budget. So what we have is the set of interventions per school buildings and facilities. We have the cost of each one of these interventions and the increase in BQI for each one of these interventions. And then we apply an optimization algorithm with the objective of maximizing the total sum of the portfolio quality building quality index with several constraints. For example, a limited budget or a maximum or a minimum BQI that I want to set to define for a particular set of buildings. And the result of this process will be the optimal set of interventions. So we can analyze the problem in parallel for the 2 decision profiles. For a maximum budget that I fixed of $50 million, we can identify that applying this algorithm, we will have a distribution of interventions, and we will have a cost of those interventions and an increase of BQI. In this case, what we can see is that with around 28% of investment of the total cost of implementing all the interventions, we will achieve 84% of the total possible benefits that can be achieved. And when we analyze with the other decision profile, we can see, for example, that the distribution of intervention changed. For example, in here, we can see that seismic intervention number increased in relation to the other decision profile. The total number of intervention in this case decreases. And what we can see is that the cost will be the same because that's the maximum budget that I established, but the delta BQI will be different. Now we are talking about 68% of the total BQI improvement or maximum improvement. So in that sense, what we have is in a graph for a particular budget constraint, the level of maximum benefits or building quality index. But anyone can ask, like, okay, you define this for 50 millions, which is 30% of the 174 millions. What if I selected 100 millions or $25 million? So in that sense, what we did is to parameterize this optimization model and run the model with different level of budget constraint. And we can then obtain this type of optimal or more efficient frontiers that we can understand. And how can I use this information? Well, there are several possibilities. One can be, for example, trying to obtain the tangent line in this curve to identify the optimal or the more efficient point for the investment. For example, in this case, for the decision profile 1, we can see that with around 10% of the investment, I can achieve around 53% of the benefits. So just with 10% at the beginning of the curve, I will gain almost half of all the possible benefits. So we can take some decisions, for example, in this case, of how much money do I need to invest in a particular portfolio. So as I mentioned before, there is no use of retrofitting, for example, of all the buildings. We can allocate the budget wisely, and we can therefore retrofit only the buildings that need retrofitting. We can do something similar for the decision profile 2, in which we want to increase the safety as much as possible. And in here, what we have is that with 7.5% of the total investment, we will have around 36 percentage of all the benefits, which is pretty good. And this information can be used to take decisions. Just to finish this, we can also see how is the distribution of the investments. You can see in green the distribution of investment for the decision profile 1, in which the size of the bar depends on the type of intervention. The darker one is the functional intervention at school level. The next one is the functional interventions at building level. And we have in this more clear green the seismic intervention. So we can see, for example, that when I use the decision profile 1, when the resources are low, I am prioritizing, of course, the functional interventions. And the opposite occurs when I am analyzing the problem with the decision profile 2, in which when resources are limited, we can see that almost all or the majority of interventions will be seismic intervention, because I am giving more weight to the safety. We can analyze this by each one of the type of interventions. We can see, for example, in here that for the seismic intervention, as I mentioned before, in the functional profile, we have a very low percentage at the beginning, and the opposite for the decision profile 2 for safety decision profile. But at the end, this will result in the same distribution. And this is because if I have unlimited funds, it doesn't matter the decision profile that you have. At the end, you will invest all the money, and that will result on the distribution of investment. And this can be seen also for the functional interventions at building level and for the functional interventions at school level. So just to conclude, this is a methodological approach for decision-making framework. It is comprised by 4 models. As I mentioned, the first one is the data processing or collection, the building quality index, then a clustering procedure, an interventions definition, and finally we finish with the optimization component. The objective is to maximize the quality, and what I want to make like a very, very important emphasis is that what we want to do with this decision-making profile is to allocate the budget wisely. And at the end, what we will have by applying this methodology is the optimal set of interventions to be implemented in a school portfolio. But of course, there are some limitations, and it's very important to mention that this is not a purely data-driven process. This is not a button that you click on it and you will have this optimal set. This relies on expert judgment. You need to apply expert judgment in all of the steps or in each of the 4 models. And it's very important to understand this method as an aid for the decision-making process rather than a replacement for the decision-making process. So it's very important to always have in mind that this requires input from experts and from decision makers. And just to finish, there, of course, there is a lot of future work that can be done based on the research that I have just shown to you. For example, we can see that there could be other type of non-additive utility functions that can be implemented into the decision-making framework. There can be, for example, other type of clustering procedures for other type of data. If we don't have the taxonomical data, we can then use other type of data, maybe continuous data, to use in this clustering procedure. There should be analyzed also, or there can be analyzed interconnection between interventions. So that consideration that I mentioned in model 3 can be overcome, consider this type of interconnection. For example, applying various interventions at the same time will reduce the cost and may also increase the benefits. And also the time dimension. What I have shown to you today is for a particular moment of time with a particular budget, but I can also include this in a process of applying this method for several years, for example, for a budget that is not fixed for one moment, but rather for a time or a frame of different years. And also this method can be applied to other type of infrastructure context, for example, hospitals or bridges. Which is part of ongoing investigation in the university with other PhD students and in other type of projects. So thank you very much. This is all. I will be happy to answer any question. I don't know, Arash, if you want to take the word.
Yes, perfect. Thank you very much. Very interesting, and definitely a very useful tool for the future. I like the fact that you pointed in the first slides that the Sendai Sustainability Development Goals is not just that, every one of them relates to each other, so very important. As usual, everyone, if you have any questions, please feel free to unmute yourself or write it in the chat. I will read it aloud. One thing before people get into questions, I'll ask this, that have you considered climate change effects? So one of the big issues is like the rise of temperature, and then that rise of temperature is causing heat stress. So people are using more electricity, and that causes functional interruption to schools. Have you considered these in the clustering decision makings?
Great question, Arash. And as I mentioned also, that's one of the barriers for quality education. And it's very, like as established by Educate a Child, climate change is by itself a barrier in the sense of higher temperatures, but also, for example, higher sea level rise or the type of effects. So today in the presentation, I only show the Cali case study with some particular consideration. But the method, of course, can be extended into other type of hazards related to climate change. We can consider, for example, if we are analyzing climate hazards, for example, hurricanes, and how high category hurricanes will increase in the future. This can also be, of course, included in the method. And that's the idea of this method, is to be as extendable and as dynamic as possible.
Yes, for sure. It should go toward multi-hazard as well. I'm just reading some questions from chat. Diana is saying, can this methodology be extrapolated to houses, probably residential?
Sure. Well, I think that this method can be applied to other type of infrastructure, including houses. What we need to do in that case is to use a different quality index with different type of attributes. What we need is the information of those houses in a particular region, and to target the interventions into solving the particular housing problems rather than the educational problems.
Yeah, the data collection of residential buildings will be much more challenging than the schools.
Exactly.
Dina, if you want to ask your question first, and I'll go to Pablo's question.
Thank you very much, Arash, for giving me the words, and thank you very much, Rafael, for a very, very interesting presentation, and for all the work, which is quite interdisciplinary and very well connected together. The thoughts process and the rationales are very clear and can be very easily followed. I just wanted to ask you, maybe it's almost a follow-up from the previous what comes up from the previous question, and i.e. the need for data in order to develop this type of information, or to apply this type of processes. and how that data can be obtained or can be had by Ministry of Education, for instance, and how it can be used. And the other questions, and I'm sorry because I then have to leave in 3 minutes, it's about whether you have actually had the opportunity of presenting these procedures to decision makers and have their feedback in terms of how they would go about it.
Thank you very much, Dina, for your words and for the questions. Regarding the first question about the data collection, I think that's one of the most important steps. What I tried to solve, or to more than solve, to research in this PhD project was, once I have this data, how can I use it to make better decisions? But it is very clear that if the information that I have is garbage, the result will be garbage too. So it's very important to improve the data collection process. And at the end, this can be extended, as we talked with Arash, to other type of hazards or for climate change. But at the end, if I don't have the information to assess that with good reliability, with less uncertainty, then there will be no sense to include that information. So I think that the data collection process should be improved, and at the end, this should be a task that can be done together with national entities, but also with the consultancy, private sector, with academia. For example, what is at this moment, what has done in the GLOSSy framework, for example, establishing data collection forms and standardizing this process is very valuable in that sense, to use information that will be reliable and important to apply this type of methods. And in relation to the second question, I think that's a next phase that should be done in this process. I was focused mainly on how to develop all the technical details behind, but of course this need to have a second phase in which we present this method to decision makers and also have their input, because as I mentioned, the weights that we use in Model 1 depends on the decision makers. And therefore, there are several methods to obtain that. You can apply an analytic hierarchical process, for example, to obtain that method, and you will need the input of the real decision makers for that. So I think that's a next step that can be used or developed for this decision making framework.
Thank you very much for your answer.
Thank you, Dina.
Okay, I'll go back to Santiago in a second. Pablo is asking, what is your approach for estimating unit cost for each intervention? This is my question as well. Am I right in the fact that you're assuming, let's say, a similar approach for all the retrofittings for all of the buildings, considering the location that you're doing?
Exactly. Well, that's a very good question. What we did in here is, once we define the cluster, we have, for example, several buildings with similar characteristics. So we obtain one building that will be the index building that we have implemented, like in other type of projects. So this building, for this particular building, we will design a retrofitting system, with having in mind that should be a retrofitting that is not for that particular building, but can be applied to all the buildings in that portfolio. And at the end, you can obtain the cost of retrofitting that index building that represent the cluster of all the buildings, and then divide it into the area of that index building. And you will have a good estimate of the unitary cost that then you can apply to other buildings by multiplying that unitary cost to the actual area of each one of the buildings.
Yes, makes sense. And Santiago, if you want to unmute yourself and ask your question.
Hello, Rafael. Muchas gracias. Thanks for your expertise. Your model is patently very well thought out, and there's been a near overabundance of data, in support of your presentation. And I was just wondering if any of your indexes included some measure of the negative impacts of bureaucracy on implementing the systems that you suggest, particularly in countries in South America, from Uruguay to Colombia. There's incontrovertible evidence that corruption and the principal agent problem contributes to a friction that makes progress difficult. Do your models include such data?
Thank you, Santiago, for your comments and for your question. And I think that that's very relevant question considering the context of in general, all developing countries. In here, I am not particularly assessing the agents and how they will impact in here. What I am considering in this method is only the decision maker preference rather than the decision maker abilities in here. We are like targeting a particular problem, but of course I think that once we obtain, for example, the results of this model, the next step is the application, and for this application we need to have a very good engagement with the decision makers, and that is related to what you were questioning, and is how to overcome all these problems. And now we need, for example, also to analyze the particular legal issues of doing this type of retrofitting to comply national codes and to adapt the results to the particular context. So I think that that's also something that should be done once the results are obtained. And of course, is something that is very important to consider.
Yeah, it's one of those tricky bits that you consider something, then something else comes in, and then at the end you have a massive, let's say, framework which takes ages to work.
Exactly.
And it gets more complex in decision making then as well. I'll go for the last question before we run out of time. Ahsane is asking whether this clustering, by the clustering that you're mentioning, you mean index building, or each group is, let's say, a number of these index buildings. The other question is, how do you establish the correlation between functional and safety decision strategies?
Yes, well, thank you, Asana, for your comments and also for your insights. Indeed, what we did in here is to develop clusters separate for each one of the taxonomies, try to separate the problems at the beginning. So, for example, one building will belong to a cluster associated to functional taxonomy, and to a completely different cluster for another type of hazard taxonomy. For example, if we are analyzing hurricane and building and seismic, then we will have different clusters distribution in that sense. So the idea is to have several distribution of the information depending on the target that I want to analyze. And for that, then we will have one intervention associated to each one of those clusters. So each building will not have the same set of intervention of the building besides, because it will depend on its particular characteristics. And the second question is the correlation between functional and safety decisional strategy. So in here, the correlation, how it's done, is through the multicriteria utility function that we developed in model 1, that's associated to the building quality index. So in there, any intervention should be assessed in the improvements or also the decreases in each one of these attributes. So it's important to understand like the problem holistically. If, for example, for retrofitting a building, I need to change the windows and make a wall, then I will have a negative effect in other type of attributes such as ventilation, for example. So at the end, when I talk about this delta in the building quality index, this delta should be or can be also a negative delta if the impacts in other attributes are greater than the impacts, that the benefits in the ones that I am targeting. But that's also something that should be addressed in future work, and is that there's no considerations when we sum that those two attributes that come from a different nature. So, for example, one may think that safety could be related in some sense to other type of attributes, or that, I don't know, the student density will be related to the bathroom density, and I cannot sum each one by separate. And maybe I should sum or take out, for example, some multiplication or some factor of the multiplication of there. And I think that could be easily done in modifying this building quality index, but at the moment is not considered in the project.
Perfect. The flexibility that the framework has, it definitely helps a lot, and you can apply it in different contexts, in different countries, for different typologies. So thank you very much. Very interesting, and hope you're successful in expanding this, and hopefully all governments start using it. If you are interested in this classification of vulnerability functions, please join us in a workshop that we will have on 18th to 19th of July. You can register in EPICentre's webpage. It's about the GLOSSy as well. It's part of the UNESCO chair in disaster risk reduction and engineering resilience. So again, thank you very much for joining us. As always, the recording of this, if the speaker accepts, will be available on EPICentre's YouTube channel. Thank you very much, and see you later.
And thank you all. See you.
Thank you. Bye.
Thank you.